Okay, so let's begin with atomic structure. The structure of atoms, rather. Atoms are composed of a tiny, dense, positively charged nucleus, which contains protons and neutrons. Together, they are termed nucleons. And it's surrounded by negatively charged electrons, whose electrostatic attraction to the nucleus provides the binding. Nearly all the mass, more than 99.9% of it, is found in the nucleus because a proton or neutron has a mass of approximately 1.66 times 10 to the minus 27 kilograms, while an electron has a mass of 9.11 times 10 to the minus 27 kilograms. We, of course, don't measure the mass of the protons and neutrons in kilograms, but instead create a new unit called the atomic mass unit, and we say that a proton and a neutron have approximately 1 AMU each, whereas an electron has about 1/2000th of that, which is negligible. A typical atomic radius is 1 times 10 to the minus 10 meters, or 1/10,000,000th of a meter, while the nuclear radius is 1 times 10 to the minus 14 meters. That's 1/10,000th as wide, and this is comparable to an orange in the middle of a football stadium. So the atom is overwhelmingly empty space. That this is concentrated in the nucleus was demonstrated via Rutherford's alpha scattering experiments. Alpha particles passed through, but a few were strongly deflected when they were fired at a gold leaf, which was just a few atoms thick. We denote nuclides using the notation of a large uppercase X and then an A and a Z in front of the X. The A is superscript, the Z is subscript, and the large X is for the chemical symbol. For example, for hydrogen it would be a capital H, for chlorine it would be Cl, the C is capitalized, the L is not. And then what is the A and what is the Z? The A is the mass number of the nuclide, and the Z is the atomic number, or the number of protons of the nuclide. And a neutral atom, for a neutral atom, the number of protons is equal to the number of electrons. So example nuclides would be C612, which is carbon 12, and U23592, which is uranium 235. Carbon 12 and carbon 14 are isotopes of carbon. They have the same Z, and nuclides with the same Z have different neutron counts, but their chemical behavior is the same, because chemical behavior is determined by the electron arrangement. But their physical and nuclear properties differ. Okay, so a word about electrons. Electrons occupy quantized energy levels. That's shells, which are principal quantum levels and not in between. In simpler models, the shell capacities are 288, 1818, and 32, and then another 32 after that. But in reality, the picture is a little bit more complicated than that. They absorb specific photon energies to move to higher levels, or emit photons when returning. So let's see here. Okay. So all these atomic scale facts that are just outlined, the sizes, the mass distribution, the notation, the isotopes, and the quantized electron shells, these underpin practical techniques and phenomena like mass spectrometry, radiometric dating, and nuclear fission applications. So let's now move on to states of matter and particle motion. So matter is modeled as particles, which are atoms, molecules, or ions, and is arranged in our everyday experience as solids, liquids, or gases, based on the competition between thermokinetic energy and intermolecular electrostatic forces. Solids form regular, dense lattices where particles vibrate about fixed positions, which, on the macro scale, confers fixed shape or volume and facilitates thermal conduction via vibrations of the lattice, while liquids retain high density and close contact but lack long-range order, allowing particles to translate and flow. And we can use this fluidity in hydraulic braking systems, for example. But anyway, gases feature particles moving randomly at high speeds, e.g. air molecules in the air that's around you right now, even when apparently still, are moving at an average speed of 500 meters per second. That's at room temperature. They have large separation distances that imply negligible interparticle forces, resulting in really, really low density, 1,000th of condensed phases like solids and liquids. And they have high compressibility, which we can use in pneumatic drills and canisters. And what is pressure? Pressure exerted by the rate of change of momentum during collisions with container walls. Let's see. Okay, so now to speak a little bit about density. Density, we symbolize that by the Greek letter rho, which kind of looks like the letter P, but is not the same thing. And it's defined as the mass per unit volume. So the equation looks like rho equals m over v. Density equals mass divided by volume. It's determined by particle mass and packing efficiency, typically following the pattern that the density of solids is greater than the density of liquids, which is much greater than the density of gases, with the critical practical exception being water, where ice's open hydrogen bonded hexagonal lattice renders it less dense than its liquid counterpart, allowing ice to float and insulate aquatic life. We also see changes of state, changes between these physical states. There's melting and freezing, depending on which way you're going, between solid and liquid. And there's boiling and condensing, depending on which way you're going, between liquid and gas. And those are physical reversible processes where mass is strictly conserved because the number of particles remains invariant, and energy supplied during these transitions overcomes attractive forces, increasing internal potential energy rather than kinetic energy or temperature. And it's observable on graphs as those flat plateaus on experimental heating and cooling curves, which show latent heat. But there is a third one, and that's sublimation, which involves a direct solid to gas transition. For example, solid carbon dioxide or dry ice sublimates at negative 78.5 degrees Celsius at atmospheric pressure and is used in cold chain logistics and iodine crystals forming purple vapor. That's another example. And they don't exhibit a liquid phase unless you dramatically increase the atmospheric pressure. Under those conditions, you might be able to see liquid carbon dioxide. Okay, so let's now move on to, I think there are a few more things I want to say about density. It's an intrinsic material property quantified in kilograms per cubic meter. That's the unit for density. Or you may use grams per cubic centimeter. And the conversion factor is that 1,000 kilograms per cubic meter is equal to 1 gram per cubic centimeter. And it determines whether or not an object floats or sinks based on the relative density to the surrounding fluid, with water typically having a density of around 1,000 kilograms per cubic meter. Now, how do we determine density? Well, this requires precise measurement of the mass via electronic balances, and you then need to determine the volume. You can use elementary geometry if you have an elementary geometric shape like a cube of a certain metal, or you can use fluid dynamics. So let me just elaborate upon that point. So like with a steel cube, the dimensions are measured using vernier calipers or micrometers to minimize zero error and calculate, and then you just apply geometric formulae. But for irregular solids, like consider a knight from the game of chess, you wish to measure the volume of such a piece, which is a highly irregular solid. You can determine the volume via displacement using a eureka can, where the volume of water displaced into a measuring cylinder is equal to the object's volume. This is called Archimedes' principle. And liquid density is found by measuring the mass of an empty measuring cylinder, adding liquid, and then subtracting the tare mass, then dividing by the volume read at the meniscus eye level, the meniscus, to avoid a parallax error. So you can use these techniques to identify unknown substances, like checking the purity of gold, and in engineering applications like load-bearing limits in construction. That's where you can use them. Now let's talk about changes of state and energy. So, thermal energy transfer changes internal energy via temperature rise or state change, and it's governed by specific heat capacity and specific latent heat. Specific heat capacity is symbolized by a lowercase c, and specific latent heat is symbolized by an uppercase L. Specific heat capacity is the energy required to raise 1 kilogram of a substance by 1 degree Celsius. So you can think of it as the resistance or the stubbornness of the material to changes in temperature. And the familiar formula is delta E equals m times c times delta theta. Now, what's an example? Well, the key example is water, which has a notably high value of C of approximately 4,200 joules per kilogram Celsius, and that makes it ideal for central heating systems and coolant in car engines, as it stores vast energy with minimal temperature fluctuation. Unlike copper, whose value of C is 390 joules per kilogram Celsius, which heats very rapidly and also loses heat very rapidly. When a substance reaches its melting or boiling point, energy input no longer raises temperature. The kinetic energy remains constant, but instead breaks into molecular bonds, increasing potential energy, and that's defined as specific latent heat. The energy to change state is determined via the equation E equals mL. This is categorized as the specific latent heat of fusion for solid liquid transitions. Okay. Just 1 second while I get something for this. Okay. So, where was I? Oh yes, specific latent heat. Okay, so melting ice for cooling drinks absorbs 334,000 joules per kilogram, and vaporization for liquid gas transitions. For example, sweating cools the body, as evaporating water absorbs the latent heat of vaporization, which is about 2,260,000 joules per kilogram. And experimental determination involves immersion heaters and voltmeters and ammeters to calculate energy supplied to a known mass. Now let's speak a bit about gas pressure and temperature. Gas pressure is the macroscopic manifestation of microscopic particle collisions. Gas particles in constant random motion collide with container walls, undergoing a change in momentum, which exerts a force, as determined via Newton's second law, over the wall area. And in the aggregate, we formulate this as pressure equals force divided by area. The temperature of a gas is a measure of the average kinetic energy of its particles. Hence, why at absolute zero, which is negative 273.15 degrees Celsius, particle motion theoretically ceases, although you can't actually reach that in practice. Increasing temperature increases this average kinetic energy, causing particles to collide with walls more frequently and with greater force, thereby linearly increasing pressure if volume is constant. That's Gay-Lussac's law. A principle explaining why aerosol cans explode in fire and car tire pressure rises after highway driving. Conversely, if volume decreases at constant temperature, pressure increases. That's Boyle's law. PV is constant. Pressure multiplied by velocity is a constant. So as I was saying, conversely, if volume decreases at constant temperature, pressure increases solely because particles collide more frequently with the reduced wall area, a relationship exploited in bicycle pumps and syringes, where reducing volume creates high pressure to force fluids. Experimentally, this linear relationship between pressure and inverse volume, or pressure and temperature in Kelvin, validates the kinetic theory. Okay, so let's just see here what the time is. Now let's move on to forces. So I'm going to open by speaking about scalars and vectors. Physical quantities in the real world are strictly classified as scalars or vectors. Scalars are magnitude only, for example, distance, speed, mass, energy, and time, whereas vectors are magnitude plus direction. They have a magnitude and a direction, e.g. displacement, velocity, acceleration, force, weight, and momentum. That's a distinction mandating that vectors be treated geometrically rather than purely arithmetically. Distance is the scalar path length, while displacement is the vector straight line change in position. Consequently, a runner completing a 400-meter oval lap covers 400 meters distance but has zero displacement, and a satellite orbiting at constant speed undergoes continuous acceleration because its velocity vector changes direction, requiring a centripetal force. Vectors are graphically represented by arrows, length scaling to magnitude, and they're combined via the tip-to-tail method, as you've seen in the diagrams we've been using. And it means that orthogonal forces of 3 newtons and 4 newtons, for example, would yield a 5 Newton resultant as derived from the Pythagorean theorem. And the bearing can be derived via right triangle trigonometry, the arctangent of 4/3, if you like. While equal opposing forces cancel to zero, which results in equilibrium. This directionality is critical in analyzing motions and forces. It distinguishes mass, which is a constant scalar, from weight, which is a gravity-dependent vector. W equals mg. Remember that from before? And it allows the subtraction of vectors to find relative velocity. So the example I've been using a lot is a headwind reducing ground speed. And it also permits the resolution of a single vector into components, such as splitting a projectile's velocity into independent vertical and horizontal vectors, or calculating the parallel component of a weight being pulled, pulling an object down a ramp. Now, let's speak about distance, displacement, speed, and velocity a little bit. Motion is quantified via the scalar-vector dichotomy, where distance is the scalar path length and displacement is the vector straight line change in position, having magnitude and bearing from the origin. Speed, which is a scalar, defines the rate of distance coverage, whereas velocity, which is a vector, specifies speed in a defined direction. Thus, an athlete running a 400-meter oval track at a constant 5 meters per second has a constant speed, but a continuously changing velocity due to the changing direction. And upon finishing, the athlete has covered 400 meters distance, yet achieved zero displacement. The fundamental governing equation is that speed is equal to distance over time, so s equals d over t. That's for the scalar situation, but for the velocity situation, v equals s over t. Velocity is equal to displacement over time. It's typically applied to constant motion. For variable motion, average speed must be calculated as total distance divided by total time, a critical distinction for multi-stage journeys where stops significantly reduce an average. You must internalize order of magnitude speeds for estimation and sanity checking calculations. So you must commit to memory and know by heart that walking is at around 1.5 meters per second, running around 3 meters per second, cycling 6 meters per second, and cars on highways 30 meters per second. Furthermore, you must know that the speed of sound in air is approximately 330 meters per second, whereas the speed of light in a vacuum is exactly 299,792,458 meters per second, or roughly 3 times 10 to the 8 meters per second. Relative velocity is vital for collision avoidance and relies on vector subtraction. Two cars converging head-on at 30 meters per second have a relative closing speed of 60 meters per second, whereas a car overtaking another, 32 meters per second versus 30 meters per second, has a relative speed of only 2 meters per second, which is intuitively obvious. Now let's speak a little bit about acceleration. Let's think about that. Acceleration is the vector rate of change of velocity, calculated as v minus u over t, where v is final velocity, u is initial velocity, and t is of course time. And it's measured in meters per second squared. It's physically interpreted as a change in speed of 1 meter per second every second. Positive acceleration implies speeding up in the direction of motion, while negative acceleration or deceleration implies slowing down or reversing direction. In scenarios where time is unknown, the time-independent equation v squared minus u squared is equal to 2as connects displacement, which is symbolized by s, directly to velocity changes, and this relationship dictates that braking distance is proportional to the square of speed, meaning doubling a car's speed from 30 miles per hour to 60 miles per hour actually quadruples the distance required to stop. And if it were to be 3 to 9, 4 to 16, and so forth, it's a quadratic relation. Near the surface of the Earth, all objects in freefall experience a uniform gravitational acceleration, symbolized by g, of approximately 9.8 meters per second squared. Often, 10 meters per second squared suffices in an exam situation, say. So this means that a dropped object accelerates to 30 meters per second after 3 seconds of falling, irrespective of mass. That was Galileo's principle. But the sort of easiest way to think about it is, if I have a stone and another stone, and they're like that, why, are you really claiming that if these stones were somehow glued together, then it would fall faster? You see? You can sort of infer it that way, but one experiment is worth 1,000 experts' opinions, as they say. However, in the real world, fluid dynamics, air resistance, increases with velocity until it balances weight, resulting in zero resultant force and zero acceleration, a state known as terminal velocity. For a skydiver, they would reach about 50 to 60 meters per second. Okay. Now, let's say a word about Newton's first law. Newton's first law asserts that velocity, both speed and direction, remains constant unless acted upon by a non-zero resultant force, a principle describing inertia that contradicts our friction-dominated intuition, where objects seemingly naturally slow down. So it was quite a radical claim to make back in the day. A zero resultant force, or equilibrium, encompasses two distinct physical states: static equilibrium, where an object at rest, like a book on a table, where upward normal reaction force exactly cancels the downward weight, and dynamic equilibrium, where an object is moving at a constant velocity, like a car cruising at 70 miles per hour, where engine thrust exactly balances air resistance and friction. Consequently, the presence of motion does not imply a force, but a change in motion does. If a vehicle turns a corner at a steady speed, the first law dictates a resultant force must be acting centripetal force via friction to change the velocity vector. While a skydiver falling at terminal velocity accelerates zero amounts, precisely because air resistance has increased to equal their weight, yielding a net force of zero. Now, that's Newton's first law. What is Newton's second law? Newton's second law quantifies dynamics via the governing equation of F equals ma, and it establishes that acceleration is directly proportional to the resultant force and inversely proportional to mass. The crucial thing here is that F represents the net vector sum of all forces, not merely a single applied force. For the calculation, mass must be in kilograms, not grams, and force in newtons, and acceleration in meters per second squared. This means that a 1,000 kilogram car with a 5,000 newton engine force and 2,000 newtons of resistive force experiences a net 3,000 newtons, resulting in an acceleration of 3 meters per second squared. This law explains why a loaded lorry accelerates more slowly than an empty one, given the same engine power. Increased mass reduces acceleration, and why braking distances increase with speed. Higher energy requires larger force or distance to decelerate the mass. It also governs rocket launches, where, as fuel is burned, mass decreases, causing acceleration to increase rapidly even if thrust remains constant. Okay, we'll wrap it up there.